Okay, so now I'm going to talk about the exact ordinary differential equations. So what is the exact ordinary differential equations? We are talking about the first order ordinary differential equations. So in those first order ordinary differential equations, uh, sometimes you can write the equation in the differential form like this. So for example, if you have this equation m x y dx plus n x y dy is equal to 0. So we have this kind of equation. So what are these m and n functions? We know that dx and dy are differentials, and these m and n are some functions both in terms of x and y. Okay, both in terms of x and y. So, but well, it's not. It is the most generalized form in this situation. It is not necessary that m have to be in both x and y. It can be either in y, or it can be either in x, or in both. So all the possibilities and all the generalizations are possible. So this type of equation will be called as an exact equation if we take the partial derivative of this function y with respect to for partial derivative of this function m with respect to y, and then if we take the partial derivative of this function n with respect to x, if both are equal, then that equation will be called an exact equation. So if this condition is met, then we have a very good method to solve this kind of this equation. Okay, so it will be better, I think, if I show you the example to solve it. I'm not going into those mathematical proofs. I will be focusing more on the example. So let me show you the example. Okay, so example. So let's take one equation which will be 2xy dx plus x square minus 1 dy is equal to 0. Okay, so now if you look at this equation, so then you can first thing you can observe that I think this equation you can easily make it into the separable form. So if you can make it in a separable form, then you can use that method to solve it. But let's not do it. Do by the method of separating the variable right now, because we already have learned that method. But one thing I want to mention over here is that we can also solve this equation by the exact equations method, which I am going to explain it now. So for some types of exact equations are also separable equations, just like this equation. But some types of exact equations will not be separable equations. So in those situations, you will only use the method which is specifically for the exact equations. So for this, I think we have to first check whether that equation is exact or not. So in this case, then this will be something which is with dx, that will be the m function, and something which will be with dy, that will be the n function. So as a first step, you will take the partial derivative of m with respect to y, okay, not x, okay, m with respect to y and n with respect to x. Okay, so I think you already understand the principles of the partial differentiation. So when you take a partial derivative, when you take a partial derivative of a function, then you consider that variable with respect to which you are taking the derivative. So for example, m is actually a function of x and y, okay, by definition. So if you are taking the derivative of m with respect to y, then in that situation you will consider x as a constant. Okay, so partial m over partial y will be taken by will be this derivative. So m is 2xy over y. So in this situation, 2 is of course constant, and x will be also considered as a constant because we are taking the derivative with respect to y. So in this case, the derivative will be 2x. Okay, because the derivative of y with respect to y will be 1. So 2x is a constant coefficient. So this is partial m over partial y. The second derivative which you will take will be the n. Okay, so partial n over partial, now n with respect to x. Okay, because to meet the condition of the exact equation, partial m over partial y should be equal to partial n over partial x. Okay, so now you have partial n over partial x, so partial x square minus 1 over partial x. So now it should be with respect to x. So in this case, by chance we don't have any y term in this case. So derivative of x square minus 1 with respect to x is then 2x minus 0, that is 2x. So now we can see that partial m over partial y is same as partial n over partial x. So this means we can say that the above equation is an exact equation. So the condition of exact equation has met. So when we meet this equation, meet this condition for the exactness of the equation, then we have a specific procedure to find the solution. Okay, so this was the first step. Okay, this was the first step. As a second step, now we have already identified that this equation is exact, then we have to follow this procedure. Later on we will see also that some of the other examples when the equation will not be exact, then what procedure we have to follow, but that is for another example. Okay, so for this procedure to follow, next thing which we have to do is that we will say that the solution of this equation, okay, solution of this equation we can represent by a function capital F. Okay, capital F. So capital F is the solution. Okay, what will be that solution, that I am going to explain now. But the for this solution to hold true, the property of this solution is that the partial derivative of this solution with respect to x will be equal to this m function. Okay, and the another property for this solution will be that partial derivative of this function, solution function f, with respect to y will be equal to n derivative. Okay, remember that earlier we were taking the partial derivative of m with respect to y and then n with respect to x, but here we are not taking the partial derivative of m and n. We are taking the partial derivative of the solution. Okay, solution. Okay, which is the solution. F is the solution of this ordinary differential equation, and then solution of f with respect to x is this. Solution of f with respect to y is this. So we can use any of these two relationships to go further into this solution. So partial m f over x. So what is partial f over x? Partial f over x, partial f over partial x is equal to m. M is equal to 2xy. So now since this is a partial derivative, and we can, from this partial derivative, we can find this solution by the integration, because this is the partial derivative is with respect to x, so we can integrate this whole expression, with respect to x. So when we integrate it, this whole expression with respect to x, then we will consider y to be a constant. Okay, y to be a constant. So let's see how it goes. So what we can do over here is that it is partial f, derivative of partial f will be equal to integral of partial f is equal to 2xy partial x. Okay, so it will be like this, and then integral of partial f will be the function itself, and now y is to be considered as a constant, so 2y will come out of the integral, and then it will be the x partial x. Okay, so the function will be then 2y x square over 2 plus some constant. Okay, but in this case we know that f is a function of x and y. Okay, so in this case, if we are integrating with respect to x, so we can take that constant as a function which will be a function of y, because y will be a constant with respect to this integration over here. So although we are adding a constant, but that constant will be a function of y in this case. Okay, will be y in this case. So we can simplify it like x square y, okay, 2 cancels with 2 plus g of y. So we have now got the function in the generalized form like this. Okay, well, this is the function. Okay, this is the solution function, but in this solution function we still don't know what is g of y. So to find what is g of y, what we will do is that we will take the, from this expression we will take the we will differentiate it with respect to y. Earlier we were using the differentiation with respect to x, and then we are now differentiating with respect to y. Why we are going to do it? Because we already know that the value of partial f over partial y is equal to this n function. Okay, n function, which is this one. Okay, so if we differentiate this function with respect to y, and then we will equate it with the known n function, we can find the value of gy. So in this case, partial f over partial y is equal to what? Is equal to, so we are going to differentiate it with respect to y. So it was y. So x square will be a constant, so it will be x square plus g, the derivative of g will be represented by g prime of y. Okay, so this is the partial f over partial y, but we also know that partial f over partial y is equal to n, and n is this which function? N is this function, n is x square minus 1. N is equal to x square minus 1. X square minus 1. So now we can compare these two values. So x square is same as x square. So this means that if these two equalities to hold true, so g prime of y should be equal to minus 1. So if g prime of y is equal to minus 1, so therefore g of y will be equal to minus y from the integration. Okay, we are going to integrate it with respect to y, because this is a function in y only, so we can integrate it with respect to y, so it will be minus y. Therefore our answer is a function f. So what is that function? X square plus y, x square y plus the function gy. So it is gy is minus y, and then we will equate it to a constant. Okay, so in this case, for example, if we are integrating over here, it will be also equal to constants. Constant will be on that side, constant will be on that side as well. So by the procedure of this method, we can say that this equation is equal to the function will be equal to a constant. So therefore x square y minus y is equal to constant is a function. So with some simplification, we can write this function as y is equal to c over x square minus 1. So this solution holds true for all the values except x is equal to 1.